Welcome. We are here with Professor Leon Koopmans from Kapteyn Astronomical Institute. I want to thank you for taking this interview with us.
Thank you.
In your talk, you spoke about gravitational lensing. Would you please explain this phenomenon to our viewers and maybe tell us why it's so important for current dark matter research?
So gravitational lensing is something that actually started with Albert Einstein for the first time. So of course he came with general relativity, and general relativity says that if you have dark matter or matter in general, even energy, it curves space and time. And so if light travels through space and there is matter in it or even energy in it, it doesn't move in a straight line, but it actually moves in curved lines. Now the universe is filled with interesting objects like galaxies, and galaxies are massive, so they also curve the space around them. And so light that comes from behind those galaxies will not move in a straight line, but will be bent, just like my glasses bend light to focus in my eyes. Gravitational lensing bends light from background objects into an image that looks slightly different than what it would look like without this galaxy in front. Now the nice thing of gravitational lensing is that it can sometimes create multiple images. So the bending of light is so strong that it doesn't make one image but two images or four images. And we can see those around galaxies. And the other nice thing is that lensing is not just sensitive to the mass that we can all see, for example made of gas or stars, but also so-called dark matter. So gravitational lensing is an extremely powerful method to sort of see dark matter in galaxies that we would otherwise not see. So that makes it very interesting as a tool to study the dark matter, and of course this is one of the topics of the conference, to study dark matter in these galaxies, because as I often say, it lights up the dark matter. It's like having a street lamp lighting up what's below it. The fact that you have a bright object in a distant universe, the dark matter, even if the galaxy would be completely dark, would still distort that light, and you would know this dark matter is there. So I think therefore it's one of the most interesting ways of studying dark matter in the universe. In particular on very small scales, this is a topic I work on as well. You can actually measure dark matter on very, very small scales with strong lensing. Techniques, let's say, other techniques have much greater difficulties with that. So that makes it very exciting to me.
Professor, can you tell us if there are any active missions currently detecting gravitational lensing events, or if there will be some in the near future?
So there are many sort of surveys going on of the entire sky. One of them, which is also discussed at this meeting, is the KITS survey. This is one that we are currently working on to find new gravitational lenses. In the past we found them, for example, with the Hubble Space Telescope, about 100 or 150. So this is what we call large samples. Now with the KITS survey, which is about 1500 degrees in the sky, so it's a very large area, we hope to find several thousand lenses. But the thing which really excites me is a new mission by ESA, which is the Euclid mission, which is not exactly the Hubble Space Telescope. It's a slightly smaller space telescope, but it will effectively image almost half the sky with the same resolution as the Hubble Space Telescope. Slightly less, but almost of comparable quality. And gravitational lenses are small objects. They're a few arc seconds, so a tiny, tiny fraction, let's say, of the size of the moon. They're very, very small, so you need high resolution in your telescopes to see them. So with Euclid, with this new mission that hopefully will fly in a few years' time, instead of finding hundreds of lenses or maybe 1,000 lenses, we hope to find 100,000 lenses. So we're now working with a large team in Europe to actually develop the machinery to find these lenses, neural networks, for example, to look at the images, taking over effectively from a human looking at them. We have neural networks finding and recognizing lenses and picking them up, collecting them, analyzing them, etc. So we are doing this now on simulations, but hopefully, of course, in a few years' time, we are going to find these hundreds of thousands of lenses. So for me personally, this space mission Euclid is very, very exciting. And then on the longer term, there are other instruments like the Square Kilometre Array, which is a radio instrument, which is now being built. But I think that timescale is a bit longer because the resolution of that instrument will, at least initially, not yet be comparable to the space missions. But in longer term, they will have similar sensitivity, similar resolution, and they will also find tens of thousands, if not hundreds of thousands of lenses. So these are the sort of short term and mid-long term, I think, are for me the most exciting missions and telescopes that are going to be built.
Coming to our final question. Professor, what are your thoughts on this Bright and Dark Universe workshop? Do you believe it's going to bring new conclusions on the nature of dark matter and dark energy?
So I think it's a very interesting workshop. I don't think it's going to give immediate conclusions, but I think what I get from this and what I feel in this meeting is there is a lot of new information and a lot of new data coming about dark matter, about dark energy, about tensions between different observations. One finds this, another one finds slightly different. And many of these things, both on the very large scales, you have tension which we think might have to do with dark energy. On the very small scales, we have tensions that we think have to do with dark matter. And there are more and more of these tensions coming, and of course the data has to be good enough before we can believe this, and we have to understand the systematics. So for me it's very nice meeting just to get this overview of all these new and exciting pieces of the puzzle, let's say, that come together. But what you also see is that there are a lot of new theories and ideas coming out, how to explain them. And I think in the coming years, it's not just collecting all this information and as a sort of puzzle, figuring out what it all means and that we haven't missed anything, but also to see which of the theories, if any of them, actually is able to explain these discrepancies between what we naively might think should be happening and what we actually see is happening. So I think it is, I don't expect great answers. I don't go to meetings expecting suddenly to see the light, let's say, but it's fantastic to see how new data is now streaming in, but also how many new ideas are coming out. If I went to a conference even a few years back, people would just talk about cold dark matter. Now there are so many alternatives, and even people talking about changing gravity, which is something people would not talk about even 5 years ago. Now it's commonplace to think about these things. So I think it's nice to see that people are sort of starting to think outside maybe the small box that they did 5 or 10 years ago. So that makes it a very exciting meeting to me.
Well, Professor, I want to thank you again and wish you a pleasant continuation.
Thank you.